Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll explore how to get started with Amazon Managed Service for Apache Flink, a fully managed service that makes it easy to build and run real-time, scalable, and highly available stream processing applications. We'll cover what Apache Flink is, why real-time data processing matters, and how Amazon's managed offering simplifies deployment, scaling, and operations. Let's get started. Apache Flink is a powerful, open-source framework designed for distributed stream and batch data processing. It has become one of the most popular engines for real-time analytics because of its ability to handle massive volumes of data with high throughput, low latency, and strong consistency guarantees. However, building and operating production-grade streaming applications with Flink is not without its challenges. First, state management at scale is incredibly complex. Flink's ability to maintain large amounts of state across millions of events is one of its strengths. But managing that state, ensuring durability, consistency, and fast access times can quickly become an operational bottleneck. Another major challenge is backpressure handling. In a streaming application, if downstream operators can't keep up with the incoming data, backpressure can ripple upstream, slowing down the entire pipeline. Managing and tuning backpressure behavior without introducing latency spikes or data loss requires deep expertise in Flink internals. Dynamic scaling of Flink jobs adds another layer of difficulty. While Flink supports scaling, adjusting jobs with heavy and complex state in real time without interrupting processing is far from straightforward. Resource management is another critical pain point. Flink applications need fine-tuned allocation of task slots, memory, CPU, and network bandwidth across a cluster. Poor resource planning can lead to job instability, inefficient utilization, or unnecessary costs. Then, there's the problem of handling late arriving or disordered events. In real-world systems, data often doesn't arrive in perfect order. Flink provides sophisticated watermarking strategies to handle such cases, but designing the right watermarking and windowing logic to ensure accuracy without compromising latency requires careful thought and domain knowledge. And that's exactly where Amazon Managed Service for Apache Flink comes in, simplifying operations, scaling, and monitoring, so you can focus on building streaming applications, not managing infrastructure. Amazon Managed Service for Apache Flink is designed to remove much of the operational complexity associated with running Apache Flink applications at scale. First, it provides a fully managed Flink infrastructure. That means you no longer need to spend time provisioning, configuring, or maintaining Flink clusters. Amazon handles the heavy lifting, setting up the environment, keeping it patched and updated, managing failovers, and ensuring your applications stay available and performant. The service can dynamically scale the CPU and memory resources allocated to your Flink application based on real-time workload needs. This ensures that you maintain optimal performance during peak loads and save costs during idle periods, without the need for manual reconfiguration or over-provisioning. The service comes with seamless integration with Amazon Kinesis and Apache Kafka. Whether your data is flowing through Kinesis data streams, Data Firehose, Amazon MSK, or even a self-managed Kafka cluster, you can easily connect your Flink applications without building custom ingestion pipelines. This makes it straightforward to plug into existing data streams and start processing events in real time. Additionally, high availability and fault tolerance are built right in. Amazon Managed Service for Apache Flink automatically handles checkpoints, snapshots, and application recovery. If your application or underlying infrastructure experiences an issue, the service recovers your job from the latest save point without manual intervention, minimizing downtime and protecting your stateful computations. And finally, it has full support for stateful applications. Flink's strength lies in managing large, complex state, and Amazon Managed Service for Apache Flink. Flink ensures that this state is durable, highly available, and encrypted. The service supports advanced Flink capabilities like save points and exactly once semantics, so you can build sophisticated streaming applications with confidence. To work effectively with Amazon Managed Service for Apache Flink, it's important to understand a few core concepts. At the heart of every Flink application is the idea of processing continuous streams of data. Flink applications read real-time data from streaming sources like Amazon Kinesis data streams or Kafka topics. And after processing the data, they write the results to various sinks such as Amazon S3 for storage, DynamoDB for real-time lookup tables, or even other streaming systems to feed downstream analytics pipelines. When processing data, Flink can operate in either a stateless or stateful mode. Stateless operations are simple. Each event is processed independently, with no memory of what happened before. On the other hand, stateful operations maintain information across events, enabling powerful patterns like aggregations and event correlation. Flink also supports windowing, a technique for grouping events over time. There are different types of windows that are supported. Tumbling windows group events into non-overlapping, fixed-size intervals. For example, computing the sum of transactions every 5 minutes. Sliding windows allow overlap, where events can belong to multiple windows, useful for rolling averages and trend analysis. Session windows dynamically adjust based on periods of activity and inactivity, automatically grouping events into sessions without needing a fixed window size. Windows allow you to structure unbounded streams into meaningful, finite chunks for analysis. Finally, maintaining application resilience relies heavily on checkpoints and save points. Checkpoints are automated, periodic snapshots of the application's state. They allow Flink to recover automatically after failures without losing data. Save points, on the other hand, are manual, out-controlled snapshots. You trigger them intentionally, for example, before upgrading your application or migrating it to a new environment, giving you full control over the application lifecycle with safe recovery points. Let us look at an illustration of the Flink architecture on AWS. We begin with the Flink program, which is where you define your application logic. This is the user code, written using Flink's APIs, that describes how data should be ingested, transformed, and output. Once the code is submitted, it goes through an optimizer and graph builder, which parses the program into an executable data flow graph. This graph represents the logical structure of your job, showing sources, transformations, and sinks in a directed pipeline. This graph is then handed off to the client, which acts as the interface between your program and the Flink cluster. The client plays a crucial role. It communicates with the rest of the system through Flink's internal actor system, a messaging infrastructure that enables asynchronous, distributed coordination. The client submits the job to the job manager, which serves as the central coordinator of the Flink cluster. The job manager houses several key components: its own actor system, the compiled data flow graph, a scheduler for assigning tasks, and a checkpoint coordinator responsible for managing fault-tolerant state snapshots. The job manager is in charge of orchestrating the job, scheduling tasks, triggering checkpoints, and monitoring overall execution. Distributed across the cluster are the task managers, the worker nodes that actually execute the tasks defined in your data flow graph. Each task manager contains multiple task slots, allowing it to run several tasks in parallel. Under the hood, each task manager also includes components like the memory and I/O manager, a network manager for inter-task communication, and its own actor system to communicate with the job manager. As data flows through the pipeline, the job manager deploys tasks to task managers, manages their lifecycle, and coordinates checkpointing to ensure state consistency in case of failures. Meanwhile, task managers report back with health checks, performance statistics, and status updates. Throughout the job lifecycle, the client stays connected, receiving updates, result summaries, and the ability to issue commands like job cancellation or reconfiguration. When building streaming applications with Amazon Managed Service for Apache Flink, one of the first things to consider is how your application will interact with data sources and sinks. In other words, where your data comes from and where it needs to go. Flink applications on AWS have native integration with Amazon Kinesis data streams and Kinesis Firehose. This makes it easy to ingest real-time event data without writing complex connection logic. Whether you're dealing with click streams, IoT sensor data, or financial transactions, Kinesis can act as a highly scalable and durable source that seamlessly connects to your Flink jobs. For organizations already invested in event-driven architectures, Apache Kafka and Amazon MSK are fully supported as well. Flink can consume from and produce two Kafka topics with built-in connectors, allowing you to tap into high-volume event pipelines or integrate with other streaming systems across your enterprise. When it's time to store your processed results, Amazon S3 serves as a common and powerful sink. Flink applications can write transform data directly to S3 buckets, making it easy to archive event streams, trigger downstream batch processing, or feed machine learning workflows. For operational use cases that require fast lookups or real-time dashboards, Amazon DynamoDB provides a perfect destination. You can enrich or aggregate streaming data in Flink and persist the results to DynamoDB tables, enabling fast and highly scalable key-value access patterns. Flink is also highly extensible, offering custom source and sink connectors through its APIs. If your application needs to connect to systems outside of the standard integrations, you can build and plug in your own connectors. Finally, Flink applications aren't limited to just one source and one sink. They can handle multiple sources and multiple sinks within a single job. This flexibility allows you to create complex pipelines that consume data from several systems, apply transformations, enrichments, and routing logic, and then fan out the results to different targets, all in real time. Beyond basic stream processing, Amazon Managed Service for Apache Flink empowers developers with a rich set of advanced processing features that enable building highly sophisticated real-time applications. First, Flink offers complex event processing, or CEP. With the CEP library, you can define patterns across multiple events, detecting sequences, conditions, or combinations that represent meaningful business situations. Next, stateful processing patterns form a core part of Flink's strength. Rather than treating each event in isolation, Flink can maintain and manage state across millions of events, enabling powerful patterns like event deduplication, real-time counters, and even modeling finite state machines. Stateful processing allows your applications to remember the past and act intelligently in real time. Time plays a crucial role in stream processing, and Flink provides robust time-based windowing strategies. Tumbling windows group events into fixed, non-overlapping intervals. Sliding windows create overlapping time slices, allowing you to perform rolling aggregations like moving averages. Session windows are dynamic, adjusting based on activity gaps, perfect for user activity modeling or clickstream analysis. These flexible windowing options let you structure continuous streams into meaningful, time-bound segments. In real-world streaming systems, data often doesn't arrive perfectly ordered. That's where watermarking for late data handling becomes critical. Watermarks let Flink track event time progress and properly handle out-of-order events. By intelligently managing when windows are closed and results emitted, Flink ensures that even late-arriving data is accurately processed, without excessive delays or inaccuracies. Finally, aggregations and joins enable Flink to combine and summarize massive volumes of data in motion. Flink supports real-time aggregations, computing sums, counts, averages, maximums, and more, as well as advanced joins across different streams or between a stream and a static dataset. These joins can happen in real time, windowed over time ranges, or even against batch datasets for enriching streaming data on the fly. When it comes to building high-performing Flink applications, performance optimization plays a critical role in achieving the right balance between speed, scalability, reliability, and cost. First, let's talk about parallelism configuration. In Flink, parallelism determines how many instances of each operator are executed in parallel. Tuning the setting properly is crucial. Too little parallelism can create bottlenecks and slow down your processing, while too much can overload your cluster, waste resources, and increase coordination overhead. Another key area is state backend selection. Flink offers multiple options for managing application state. For workloads with large amounts of state, such as long-running aggregations or complex session tracking, RocksDB is often the best choice because it stores state efficiently on disk. For low-latency applications with smaller state, Flink's default in-memory state backend can offer faster read and write performance. Checkpoint interval tuning is another important lever. Frequent checkpoints offer stronger recovery guarantees, minimizing data loss in the event of a failure. However, each checkpoint introduces some performance overhead. Setting intervals too short can overwhelm the system, while setting them too long can increase recovery time. Back pressure management is essential for maintaining system stability. In real-world pipelines, downstream operators can sometimes process data slower than upstream sources produce it. This can lead to back pressure, where data queues up in memory, causing increasing latencies and eventually risking out-of-memory errors. Detecting back pressure early and designing strategies to handle it helps maintain smooth end-to-end flow across your application. Finally, serialization optimization is often overlooked, but can make a huge difference, especially at scale. Efficient serialization reduces CPU load, memory usage, and network I/O. Choosing lightweight serializers and minimizing object copying during processing significantly boosts throughput and reduces garbage collection overhead, making your application faster and more efficient. Security and compliance are fundamental pillars when working with streaming data. An Amazon Managed Service for Apache Flink is built with strong security controls right out of the box. Flink applications running on the managed service integrate tightly with IAM. This allows you to define fine-grained access controls over every part of your system, from who can start and stop applications, to what data sources and sinks they can read from or write to. By assigning IAM roles and crafting precise policies, you can ensure that each component only has the minimum necessary permissions, following the principle of least privilege. Next, data encryption is enforced both at rest and in transit. Data stored in systems like S3, DynamoDB, or within RocksDB-based state backends is encrypted using strong encryption standards. And during processing, data moving between operators, between sources, and across sinks is protected with encryption protocols. This ensures that sensitive information remains secure throughout its entire lifecycle. Network security is also a top priority. Amazon Managed Service for Apache Flink runs inside your virtual private cloud, or VPC, providing network isolation from the public internet. You can further enhance security by using VPC endpoints to securely connect to services like Kinesis data streams, Amazon MSK, Amazon S3, and DynamoDB, ensuring that your data never leaves the private AWS network. Authentication and authorization extend beyond AWS services as well. When integrating with sources like MSK, Flink applications can securely authenticate using industry-standard protocols such as SASL, Scram, IAM-based authentication, or even custom authentication providers, giving you flexibility without compromising on security. Finally, for those organizations that require strong control over encryption keys, Amazon Managed Service for Apache Flink allows you to use KMS with customer-managed keys. This gives you full control over key rotation policies, auditability, and ensures your encryption practices meet internal and regulatory compliance requirements. Understanding the pricing model for Amazon Managed Service for Apache Flink is essential for accurately forecasting your operational costs and making informed architectural decisions. First and foremost, compute resources are billed based on the number of Kinesis processing units, or KPUs, consumed per hour. Each KPU bundles a fixed amount of vCPU, memory, and network bandwidth. The more intensive your application, whether it's due to higher throughput, heavier state, or more parallelism, the more KPUs you'll consume, directly impacting your compute costs. In addition to compute, there are storage charges associated with application state. This includes persistent storage of large application state, checkpoints, and save points. Storage is typically billed per gigabyte per month, so applications with heavy stateful operations should factor storage costs into their pricing model. Amazon Managed Service for Apache Flink also supports two modes: provisioned and auto-scaling. In provisioned mode, you reserve a fixed number of KPUs and pay for them. In auto-scaling mode, the service automatically adjusts the number of KPUs based on demand, helping optimize costs by scaling down during periods of low activity and scaling up seamlessly when traffic spikes. It's important to note that application runtime is a billing factor. You are billed from the time your application starts running until you stop it, even if your data ingestion rate temporarily drops to zero. Managing your application's lifecycle wisely can prevent unnecessary costs. When it comes to networking, If your Flink application accesses resources across different VPCs or uses services like Private Link, standard AWS networking charges apply. These can add up, especially in data-intensive workloads, so it's important to design your architecture with networking costs in mind. Finally, data transfer costs must be considered, particularly if your application is moving data between services across availability zones or to external endpoints. Standard AWS data transfer rates apply in these scenarios. Effective monitoring is essential to ensure that your streaming applications are healthy, performant, and resilient. At the foundation of Flink monitoring is Amazon CloudWatch. Flink applications automatically emit a wide range of metrics to CloudWatch, covering vital signals such as CPU utilization, memory consumption, KPU usage, data throughput rates, checkpoint durations, and back pressure levels. These metrics allow you to track the health and efficiency of your applications in real time and identify bottlenecks before they impact your users. In addition to metrics, CloudWatch logs capture detailed log data generated by your Flink applications. This includes system logs, error messages, user-generated logs, and runtime exceptions. Centralizing logs in CloudWatch makes it straightforward to set up searches, create log-based metrics, and troubleshoot issues quickly without manually managing servers or storage. Beyond CloudWatch, you can also access the Flink managed UI provided by the service. This web-based dashboard gives you a real-time view into your applications, showing job graphs, operator chains, task manager statuses, and checkpoint histories. It's an invaluable tool for engineers to visually inspect data flow, understand operator behavior, and detect skew or imbalance within a job. Application level and task level metrics are available through this UI as well. You can monitor input and output rates per operator, measure end-to-end job latency, and analyze checkpoint failures at a very granular level. This detailed visibility is critical for fine-tuning performance, scaling decisions, and debugging complex event processing pipelines. For governance and compliance, AWS CloudTrail comes into play. CloudTrail automatically captures and records all API interactions with your Flink applications, such as application start, stop, scaling actions, and IAM changes. These audit logs are vital for meeting regulatory requirements, conducting security reviews, and tracing operational activities. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.